This heating apparatus might be considered one of the most economical thermal solutions ever conceived. Yet its installation is forbidden in the majority of residences throughout the developed world. This is known as a rocket mass heater. It consumes 90% less firewood than a conventional heating unit, can warm a dwelling for as long as 24 hours on a solitary ignition, and can be constructed for under $500 using supplies readily available at your neighborhood hardware establishment. Its origins trace back to one of the most impoverished territories in Central America, where it was conceived not for monetary savings, but for the preservation of human lives. This is the chronicle of the rocket mass heater, its operational mechanisms, and the reasons why construction mandates have rendered its assembly unlawful for you. In the year 1973, a Welsh ecologist named Ianto Evans observed women and children perishing in Guatemalan domestic settings. The cause was neither destitution, conflict, nor illness, but rather smoke. 3 stone hearths, utilized for 4 hours each day, saturated interior spaces with particulate matter equivalent to consuming 40 cigarettes daily. Families inhaled this noxious air year after year, leading to the insidious development of chronic respiratory ailments in individuals who possessed no alternative but to continue employing the very systems that were poisoning them. According to the World Health Organization, indoor smoke emanating from open fires claims the lives of approximately 4 million people annually, predominantly women and children. Having personally witnessed this grim reality, Evans understood the gravity of the situation perhaps better than most. Consequently, in collaboration with the Aprovecho Research Institute located in Oregon, he developed a substitute system. His objective was to engineer a heating unit that any individual could fabricate from locally sourced materials, one that would combust wood with sufficient efficiency to generate minimal smoke and require no external supply chain. And in 1982, the rocket stove was introduced. It derived its name from the forceful rush of air through its characteristic L-shaped combustion chamber. It burned with greater intensity, cleanliness, and on less fuel than any predecessor. Subsequent investigations revealed that this straightforward stove design diminished carbon monoxide production within the kitchen by 1/3. It was an ingenious innovation, yet Evans perceived a fundamental flaw. When employing the rocket stove, a considerable amount of heat was lost. Energy was transferred to the cooking vessel and then dissipated into the atmosphere. In the humid environment of Guatemala, this was not a significant issue. But in cooler regions, where a stove served for both heating and cooking, this presented a considerable challenge. The resolution to this predicament originated in Korea. For over 3,000 years, Koreans had channeled combustion gases from a firebox beneath a stone floor, thereby heating the floor from below and radiating warmth for extended periods after the fire had extinguished, a system known as the ondol. The crucial lesson derived from the ondol, as well as other masonry heating systems globally, was the efficient utilization of thermal storage. This involves materials possessing the capacity to absorb heat from a brief, intense thermal source and then gradually release it over subsequent hours. By the 1980s, Evans unveiled the advanced iteration of his creation, the rocket mass heater. By integrating his highly efficient combustion stove with the thermal storage capabilities of the ondol, he had conceived one of the most economical home heating systems ever devised. To fully grasp the brilliance of this system, one must comprehend its operation. It commences with the insertion of firewood into an upright feeding tube. These are sticks ranging from 1 to 3 inches in diameter, the type of material that naturally falls from trees. Unlike a conventional stove, the combustion in this system occurs laterally. The L-shaped geometry at the base of the feeding tube redirects the flame into a horizontal burn tunnel before it ascends vertically once more. The fire then ascends into the core of the apparatus, a component referred to as a heat riser. The heat riser, a robust, heavily insulated chamber, generates temperatures between 1100 and 1650 degrees Fahrenheit. A conventional wood-burning stove, in contrast, operates at temperatures ranging from 570 to 930 degrees Fahrenheit. The heat riser captures the flammable gases released by the wood as its solid matter decomposes. In a traditional system, the majority of these gases are expelled through a vertical chimney before complete combustion. The wood gas trapped within the heat riser undergoes combustion, initiating a secondary burn and releasing additional thermal energy into the system. This combustion produces extremely hot, clean gases, primarily carbon dioxide and water vapor. As these gases begin to exit the heat riser, an inverted steel barrel is positioned over the riser, forcing the gases downwards and around the exterior of the column, thereby imparting immediate warmth to the room. At the base of the drum, the hot gas enters an exhaust duct embedded within 2 to 3 tons of cob. Due to its superior thermal properties, the cob absorbs heat from the exhaust pipe, slowly radiating it into its surroundings for the subsequent 16 to 24 hours. By the time the gases reach the outdoor chimney, their temperature has diminished to between 100 and 190 degrees Fahrenheit. For comparative purposes, a conventional wood stove exhausts gases at 750 to 1100 degrees Fahrenheit, and every degree of this discrepancy represents heat retained within the building. This system is so efficient that when a Dutch aerospace engineer measured the combustion of a rocket mass heater, it registered 90.5% thermal efficiency, establishing it as one of the most effective methods for generating heat from biomass. To provide context, an open fire possesses a thermal efficiency of 15%. While this may sound remarkably impressive, it is highly probable that few individuals utilize an open fire as their primary heating source. Therefore, how does it compare to something more familiar? A contemporary high-efficiency gas furnace is rated between 80 and 98% AFUE, a metric that quantifies the system's effectiveness in converting fuel into heat. This may appear competitive, but the crucial distinction is that AFUE measures conversion, not delivery. The inherent issue with these systems is that gas-powered central heating warms the air, and warm air naturally ascends. It accumulates at the ceiling and escapes each time a door is opened. When the thermostat detects a temperature drop, the furnace activates, and this cycle repeats throughout the day and night. In essence, you are not heating your residence, but rather the air contained within it. A system that stores its thermal energy within the mass of a 2-ton cob bench is infinitely more efficient in terms of both fuel consumption and cost. Furthermore, there exists substantial documented evidence illustrating the efficiency of the rocket mass heater. A residence measuring 900 square feet in upstate New York reported a 60% reduction in firewood consumption after transitioning from a conventional wood stove. Another documented instance in Colorado's San Luis Valley indicated a 50% decrease in fuel usage following the adoption of the rocket mass heater. The type of fuel required is no more than mere sticks. Many users report heating their homes entirely from materials accumulated in their gardens over the course of a year. Therefore, after 50 years of documented performance, why is this technology not only absent from the mainstream, but actively prohibited by building regulations in most of the developed world? The straightforward explanation is that building codes in the United States, the United Kingdom, and across much of Europe forbid open combustion appliances in residential structures. The reason for this prohibition is that within a confined environment, combustion systems such as this have been proven to be fatal. Under typical operating conditions, combustion gases travel in a singular direction, upwards through the riser, through the thermal mass, and out of the building. However, a well-insulated modern home equipped with mechanical ventilation, a heat recovery unit, or a kitchen extraction fan can develop negative indoor air pressure. When this occurs, airflow can reverse, potentially drawing colorless, odorless, and lethal carbon monoxide back into the living space without any indication. The certification framework presents a secondary impediment to the implementation of the rocket mass heater. The Environmental Protection Agency mandates that any wood-burning appliance undergo standardized laboratory testing on identical, mass-produced units. A site-built system constructed from clay, sand, and a repurposed drum lacks a pathway through a regulatory structure designed for manufactured commercial products. Consequently, in essence, bureaucratic processes render it virtually impossible for you to implement this technology in a significant portion of the developed world. However, those willing to navigate the regulatory process will discover more avenues available than a decade ago. In Portland, for instance, there is now a designated route for indoor rocket mass heaters. Rural counties across the American West, with provisions for owner-builders, can also obtain approval for indoor installations, provided the builder can demonstrate compliance with ventilation and carbon monoxide detection requirements. Nevertheless, for the majority of individuals, regulations dictate that it is unlawful to replicate this setup within their homes. In such circumstances, two options are available. The most genuinely accessible starting point is a structure that falls entirely outside residential building codes, such as a workshop, a greenhouse, or a barn. These spaces are not subject to indoor pressure concerns and allow for the acquisition of fundamental knowledge regarding rocket combustion in an environment where the consequence of a design error is a cool workshop rather than a carbon monoxide incident. If your aim is to harness the efficiency of a mass heater, then the batchbox design is among the few that align with the principles that building regulations are intended to enforce. Its sealed firebox door features a dedicated external air intake piped directly from the outdoors, effectively eliminating the risk of carbon monoxide poisoning by completely isolating the combustion process from the room's air pressure. A 6-inch batch box system incurs material costs between $300 and $700, operates without indoor pressure concerns, and facilitates the learning of rocket combustion fundamentals. Specifications for batch box construction are freely accessible online under a Creative Commons license and represent the most comprehensive technical documentation available for building your own system. The rocket mass heater is a heating system derived from 3,000-year-old thermal principles which leverages the power of 20th century combustion science. While its knowledge is easily attainable and materials are widely available, for the majority of us, regulations make its implementation impossible. Much of what this channel explores operates outside the conventional mainstream, not because it is ineffective, but because mainstream systems are more readily marketed and regulated. If the pursuit of rediscovered self-sufficiency holds significance for you, subscribing and sharing is the most straightforward method to ensure that such information continues to be discovered. And if you wish to view our comprehensive analysis of the Korean ondol, be sure to watch the video presented here.